What's up guys, it's Simon Fiaz and today's video is on AQA AS Level Chemistry Paper 1 2016. We close this tab. Question 1. Give the full electron configuration of Al atom and of a Cr3 plus ion. So Al atom, I look at aluminium and it is here. And I can see that it's clearly got 13 electrons, the bottom number. So it's going to be 1s2, 2s2, 2p6, 3s2. How many electrons is that? 2, 4, 10, 12. So I need a 3p1. And of a Cr3 plus ion. Now the thing about this is positively charged, and it's 3 plus charge. I need to minus 3 electrons from whatever chromium is. So if we look at chromium, there we go, 24 electrons. So I'm gonna have to minus 3 to get me 21 negatively charged electrons. Now if I do that, 1s2, 2s2, 2p6, 3s2, 3p6. Now how many do we have? 4, 10, 12, 18, 4s2, 20, 4p1, right? But I can, instead of saying that, what I can now do, what it's supposed to do, is say 3d3. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Deduce the formula of the ion has a charge of 2 plus the same electron configuration as krypton. Krypton. If I look at krypton, it's got 36 electrons. Now it tells me it has the same number of electrons as krypton, but it's also got a 2 plus charge. So it's actually got, instead of having 36 electrons, it's got 38, because then the minus 2 from the plus 2 charge will give me 36. So it's going to be strontium because it's got 38 electrons. It's going to be Sr 2 plus. Deduce the formula of the compound that contains 2 plus ions and 3 minus ions that both have the same electric configuration as argon. I look at argon, 18 electrons. Now if it's a 3 plus, it's got to be 18. It's got to be it's 3 minus. So it's going to have to be phosphorus because it's 15 electrons, and I'm going to add 3, which will give me 18. So it's going to be P3 minus for one of them, and the other one with the 2 plus ions, well, that's going to be calcium Ca2 plus. And what you do in this case is you just swap the charges. So instead of that, it's just going to be Ca3P2, and that's going to be the overall compound, Ca3P2. Deduce which of Na plus and Mg2 plus is smaller ion. Very classic question. Very classic question. Mg2 plus. Reason being, Mg2 plus has more protons, however, with the same shielding / number of electrons. More protons is Mg2 plus because it's got more protons, however, the same shielding / number of electrons. Run equation to represent the process that occurs when the first ionization energy for sodium is measured. So it's going to be Na gaseous, arrow Na plus gaseous, plus E minus. First ionization energies are first of some period 3 elements as shown in figure 1. Complete figure 1 plotting the approximate first ionization for magnesium and sulfur. So we need one here and one here. That's what we're trying to plot. So for magnesium, I would say anything between, because what it's going to generally look like is that, or here, then it goes up, and same thing. So for magnesium, it should be somewhere 600 to 800. So let's just say here. And sulfur, somewhere between 800 to 1000 or 1040, because then it goes back down. So here, that should be fine. Explaining why the first ionization energy of sulfur is different from that of phosphorus. Now, to answer this question, you've got to think deeply. if I look at sulfur, it's got 16 electrons, right? Obviously, in the exam, you probably go through the electron configuration, but I already know sulfur. The key fact about sulfur that the electrons are paired in the 3p. Obviously, you need to this part in which orbital, in the 3p orbital, that's really important. You can't just say the p orbital because it could be any p orbital, 2p orbital, 4p orbital. So you have to say in the 3p orbital in sulfur. And then why does that even matter? The electrons are paired, or paired electrons repel. And why does that matter? Therefore, less energy needed to remove the electrons. Sulfur electrons are paired in 3p orbital in sulfur. Paired electrons repel, therefore less energy needed to remove the electrons. Question 3. Calculate the mean titer and use it to determine the amount of moles of hydrochloric acid directly with 25 centimeters cubed of this solution. Now the mean titer, all I'm going to do is, I'm not going to add them all up and divide by 3. Classic mistake. What I'm going to do is I'm going to look for the ones that are concordant within 0.1 centimeters cubed of each other. So clearly these two. Then I'm going to add them to both up. 9.75 plus 9.65 divided by 2 because there's 2 of them. And I should get 9.70 centimeters cubed. Then use it to determine the amount of moles of HCl that reacted with this much of MHCO3 solution. So this is the mean titer with this much solution. So all I'm going to do really is I know with 25 centimeters cubed of MHCO CH3 solution, amount of moles of this. Well, moles is concentration times by volume, and I'm given the concentration here, this much, 0.102. So I'm just going to be 0.102 times by 9.70. However, 0.102 is in moles per minus cubed. This 9.70 is clearly in centimeters cubed because all of these are in centimeters cubed, and I just added those two and divided by 2. So I need to divide it up by 1,000. That's another key step. And then you should get the answer as 9.89 times by 10 to the power minus 4. And also double check if it wants you to give it to any number of decimal places or significant figures. In this case, it doesn't. Calculate the amount of moles of this in this much of solution. Well, I have got... Okay, so... Oh, right, okay. So I've got the moles of HCl that reacted with this much of solution, and I know from the equation it's a 1-to-1 molar ratio. So if I know the moles of HCl, I also know the moles of this. The only difference is this case it wants it 250 centimeters cubed, in this case it will be 25. So I just need to times. So I'm going to do 9.89 times by 10 to the power minus 4. And I'm going to times it by 10, and that should just give me my new number of moles of HCO3. 9.89 times by 10 to the power minus 3. Then calculate experimental value for the MR of this. Well, I know moles, as well as being concentration and volume, is also mass of MR, the classic equation or the formula. Therefore, to find out the MR is going to be the mass, which is this in milligrams, but I want it in grams, so I need to divide by 1,000. So it's going to be 1.464. 1.464 divided by 9.89 times by 10 to the power minus 3. And in this question, it says appropriate number of significant figures, so give it to the appropriate number of significant figures. 148 as your MR. Question 3.3. You should identify the student. Identify use of the burette as the largest source of uncertainty. just got to put a couple of things away, guys. Sorry for the disturbance. Okay, it says student identified use of the burette as the largest source of uncertainty. Suggests how the procedure could be improved to reduce using the same apparatus. Okay, classic question. Use a larger mass of solid. That's really it. Use a larger mass of solid. How does this justify it? Well, so a larger, tighter / reading will be needed. Another student is required to make this. Describe a method to prepare the solution, and this is going to be so how to make your standard solution. So stage one, transfers known mass of solid, weigh the sample bottle containing the solid on a balance, transfer to beaker and re-weigh sample bottle, and then also record the difference in mass. Stage 2, scroll down so you guys can see it. Dissolve in water. Add distilled / deionized water. We'll just say distilled water. Stir with a glass rod until all the solid has dissolved. Stage 3, transfer, washing and agitation. Transfer to volumetric flask with washings. Make up to 250 centimeters cube. Shake / invert. Question 4. In terms of structure and bonding, explain why the boiling point of bromine is different from that of magnesium, and then suggest why magnesium is a liquid of a much greater temperature range than that. Okay. First thing I would say is magnesium and bromine. Well, magnesium is metallic, bromine is simple molecular. So that's the first thing I'm going to say. Bromine is simple molecular. Magnesium is metallic. That's literally all I'm going to say. For metallic, I'm going to explain a bit more. It consists of positive ions in a sea of delocalized electrons. Not necessary, but yeah. Then what I need to say is that bromine has weak van der Waals forces between the molecules, whereas magnesium has strong metallic bonds. Hence, more energy is needed to overcome the stronger metallic bonds. So magnesium has a much greater liquid range compared to bromine. Why? As forces of attraction in a liquid are stronger. Question 5. Figure 2 represents two glass flasks, P and Q connected via a tap. Flask Q, volumes up, filled with ammonia at that pressure. The tap's closed and is a vacuum in flask P. The gas constant R is at. Calculate mass of ammonia in the flask Q. So, this is going to be very, very easy in my opinion. So I'm pretty sure all we're going to have to do is PV equals nRT. Obviously, I'm going to have to use that. Then N equals PV over RT. And pressure is 102 kilopascals, so I need to convert it into pascals. Times by the volume, but volume is measured in meters cubed, that's in centimeters cubed. So that's, I guess that's where most students would probably make a mistake. But remember, do dm cubed, and then it is meters cubed and centimeters cubed. So if I want to go from each one, I time by 1,000, but because I want to go from centimeters cubed to meters cubed, I need to divide by a million. So it's just going to be 1.0 times by 10 to the power minus 3. Over R, which is obviously 8.31, times by the temperature in Kelvin. 300 Kelvin, that's nice, it's already in Kelvin. That will give me the moles, but I want the mass. Well, moles is mass of MR, therefore mass is just going to be the moles, which I get from here, times by the MR of ammonia, which is NH3, which is 14 plus 3, which is 17. And that's it. Obviously, I'm saying it like that, but that's still a lot of steps, I guess. Then do that, and you should get 0.696 grams. 0.696 grams. Now, the second part of the question is definitely going to be a lot more challenging because it says when the tap is opened, ammonia passes into flask P. The temperature decreases by 5 degrees Celsius. The final pressure in both flasks is that. Calculate the volume of flask P. So, what I basically did is, actually no, it tells me the question flask Q has volume of that. So for flask Q, the volume is 1.00 times by 10 to the power 3 meters. Okay, it wants a volume in centimeters cubed, so times by 10 to the power 3 centimeters cubed. I don't know the volume in flask P. That's what I'm trying to find out. However, I know what I can do is I can find out the total volume in flask P and Q, and then subtract from flask Q, and then I'll get flask P. Easier said than done, but how do I do that then? Well, first thing I'm going to do, I'm going to use PV equals nRT again. But in this case, I want to find volume. V equals nRT divided by P. Number of moles of ammonia is what I worked out here, right? So, question mark, but I already know it. Times by 8.31 times by temperature, but I know the temperature decreases by 5 degrees Celsius. So what does that mean? Does that mean, no, that just means that this 300 Kelvin becomes 295 Kelvin. That's all that means. If it's a change, if it's a decrease and increase in temperature in degrees Celsius, Kelvin, doesn't matter. So it's just going to be 295 divided by the pressure in pascals, but the final pressure is 75,000 pascals, and the number of moles. That will give me the total volume of flask P and flask Q, and therefore to find out the volume of flask P, I'm just going to do whatever I get from here, which is obviously 1.34 times by 10 to the power minus 3, and obviously volume is measured in meters cubed in the ideal gas equation, so that's fine. Minus flask Q, 1.00 times by 10 to the power 3. So I need to convert this meters cubed into centimeters cubed, and again I just draw that out. dm cubed, meters cubed, centimeters cubed. So I want to go from meters cubed to centimeters cubed, so I'm going to have to times by a million. So it's just going to be 1.34 times by 10 to the power 3 minus 1.00 times by 10 to the power 3. So if I put that in my calculator, I get 340 centimeters cubed. And that is perfectly fine. Question 6. Explain how ions are accelerated, detected, and have their abundance determined in time of flight, TOF mass spectrometer. So, ions are accelerated by attraction to negatively charged plate / electric field. Ions are detected by gaining electrons, very simple, and ions abundance determined by size of current flowing in the detector. That's it. So ions accelerate by attraction to negatively charged plate / electric field. Ions detected by gaining electrons. Abundance determined by size of current flowing in detector. Calculate mass in kilograms of single 52 Cr plus ion. So what I have to do first is I'm going to do 52 divided by 6.022 times by 10 to the power 23. But I want in kilograms, and then whatever my calculator gives me, then press divide by 1000. Then divide by 1000. And I get 8.64 times by 10 to the power minus 6. 8.64 times by 10 to the power minus 26 kg. Or you could just do this times by 1000. Because you're dividing by it anyway, it's the same as, divided by that. In the time of flight mass spectrometer, the kinetic energy of this ion was this much. Calculate the velocity. So I'm going to have to rearrange the equation. So, velocity, I already know, I've memorized it off by heart, is square root of 2ke divided by m, but I'll go through how you would rearrange it. So you just times by 2, firstly, and if you do that, you get 2ke equals mv squared. Very simple. Then divide by m, so v squared is 2ke divided by m, and then square root it. So yeah, you can either memorize it or rearrange it, your choice. So you get velocity square root of 2ke divided by m. Therefore, velocity is going to be the square root of 2 times by 1.269 times by 10 to the power minus 13. That's the kinetic energy. Divided by the mass of the 52 Cr plus ion, which I just worked out in the previous part. 8.64 times by 10 to the power minus 6 in kg. I get a ridiculously large number, so I need to put it in standard form. 1.71 times by 10 to the power 6 meters per second to the power minus 1. And, remembering to put it in standard form gives me the units anyway. But always put it in standard form if you can, if it's a ridiculously large number. 6.4 bromine has two isotopes, 79 Br and 81 Br, in approximately equal abundance. In a time of flight mass spectrometer, bromine forms ions with formula Br2 plus. Sketch the pattern of peaks you would expect to see in a mass spectrum of a sample of bromine. So 158 at 25%, 160 at 50%, 162 at 25%. 158, 25%, 160, 50%, 162, 25%. Use the data to calculate abundance of isotope MXE and calculate M, the mass number of MXE. Now, the percentage abundance got to add up to 100. So to find out this, what I'm going to do is 100 minus 28 plus 25 plus 27. Very, very simple. And I get 20. Obviously, it's a percentage abundance of 20%. Now I want to find out the mass number of MXE. So what I'm going to have to do is, I know the AR equals 129 times by 28 plus 131 times by 25 plus 132 times by 27 plus 20y divided by 100. Rearrange it and you get y, and then that's really it. Yeah. And you should get mass numbers 1, 3, 4. 7.1 draw diagrams to illustrate the shapes of NH3 molecules. So NH3. So H, H, H. Remember the NH3 has got long pair of electrons as well, because then it can form NH4 plus ion, ammonium ion, AlCl3, AlCl, Cl, Cl. That's it. Indicate the values of the bond angles. Okay, so this one's just going to be 120 degrees. This one is going to be around about 107 degrees, 106 to 108 degrees. Name the type of bond between nitrogen and aluminium. Explain how this type of bond is formed. Name the type of bond. It's coordinate bond, and you need a dash in between here as well. Coordinate bond. Both electrons come from the nitrogen bracket H3. Come from the nitrogen and ammonia. Explain how the value changes, if at all, information of that. Well, aluminium is now surrounded by 4 electron pairs. That's a key fact. Aluminium is now surrounded by 4 electron pairs. It is tetrahedral, therefore bond angle decreases from 120 degrees to 107 degrees. Aluminium is now surrounded by 4 electron pairs, tetrahedral, but therefore bond angle decreases from 120 degrees to 107 degrees. Question 8.1, write a half equation for the oxidation of chloride ions. Chloride ions, Cl minus. Oxidation, I'm going to go to chlorine, but then I've got a 2 here, but then I also need a 2 minus here. And trust me, this topic of writing half equations and oxidation reduction, it is literally how much can you practice half equations. Once you've done it like maybe 100 times or hundreds of times, then you'll get the hang of it. Write half equation for reduction of chlorate ions to chlorine. So chlorate ion ClO minus to chlorine Cl2, but I've got 2 here, so I need a 2 here because I need 2 chlorines. But now I've got 2 oxygen, so I need to add what's it called, a water molecule. But I don't need to add 1 water molecule, I need to add 2 water molecules because I need 2 oxygens. But now I've added that water molecule, I've also got 4H plus ions there, so I need to add 4H plus ions here. But now that I've got 4H plus ions here, is the charges even balanced? No, it's not. So I need to think about that. And what I'm going to do, 4H plus plus 2E minus will give me overall charge of 2 plus. So I need to add a 2 negatively charged electrons. And then double check everything. I've got 2 chlorines on the left hand side, 2 chlorines on the right hand side. I've got 2 oxygens on the left hand side, 2 oxygens on the right hand side, 4 hydrogens, 4H pluses, and then 4 hydrogens, 2E minus, 2 overall charge. And yeah, that's it. Then it says write an overall equation for the redox reaction of chlorate ions with hydrochloric acid. So overall equation, what I need to do is I need to cancel out these electrons. Obviously in the exam, don't do it from here, but I'm just going to do it from here for the sake of the video. So cancel them out, and then you just add them on. So then it's going to be 2Cl minus plus 4H plus plus 2ClO minus to form Cl2 plus 2H2O plus Cl2. So it's going to be 2Cl2. So 2Cl minus plus 4H plus 2ClO minus 2Cl2s plus 2H2O. And most students will leave it like that, including myself, until I fell for the mistake. All of these are divisible by 2. That's 2, that's 4, that's 2, that's 2, that's 2. So all I need to do now is do it in its simplest form. So it's going to be Cl minus plus 2H plus ClO minus Cl2 plus H2O. Cl minus plus 2H plus 2 plus ClO minus ROCl2 per H2O. Don't fall for that mistake. It's very, very easy to fall for. Like, it's very, very easy. Question 8.4. Solution of sodium chloride 1 was added to a colorless solution of potassium iodide. Suggests what is observed. It goes brown, clearly, due to iodine, because I minus oxidize. Potassium iodide, sure, goes brown due to iodine, because the I minus is oxidized. I minus oxidized. Question 9.1, and the multiple choice questions I won't be going through for any of these videos. Go for them in a different video. Question 9.1. A student was given a powder made from a mixture of anhydrous barium chloride and anhydrous magnesium chloride. Student dissolved this in a conic flask, added excess sulfuric acid, white precipitate was formed. Now I know white precipitate was formed, so barium chloride, identify the white precipitate. It's going to be barium sulfate, because what I'm doing is barium chloride plus H2SO4. Yeah, I'm going to form barium sulfate plus, right, barium sulfate plus not H2O plus HCl, or 2HCl. Yeah, plus 2HCl. Anyway, the white precipitate is barium sulfate, so that's it. Then it says calculate percentage by mass of the magnesium chloride in the powder. So the mass of the solid is 0.764, and I want to work at a percentage by mass of magnesium chloride. So what I'm going to have to do first is, I know student dissolve this much of powder in a conical flask, add excess sulfuric acid, white precipitate form, and that was that. So I can find out the moles of barium sulfate, and then I can, yeah, so let's do that. So the moles of barium sulfate, I know the mass of the solid 0.764 over the MR. Look it up in the periodic table. You should get 233.4 total MR of BaSO4. Then that will give you the moles, which is 0.03273 moles, right? I want to work at a percentage by mass of magnesium chloride. Well, you should know that it's obviously going to be a 1-to-1 mole ratio. No, it's made from a mixture of this and this. Okay, so I worked out the moles of barium sulfate 0.764 over the MR. Then I've got the moles of magnesium chloride, and I want to work out the mass. Moles is mass over MR. Mass is just going to be times by the MR of barium chloride. Yeah, because this is going to be the mass of barium chloride, my bad, not magnesium chloride, barium chloride. Times by 208.3. That will give you 0.6818, and therefore to work at a percentage by mass of magnesium chloride is going to be the total mass 1.056 minus that divided by 1.056 times by 100. Yeah, because I worked out the moles of barium sulfate, and therefore I know it's 1-to-1 mole ratio. I work out the moles of barium chloride. Then I can work out the mass of barium chloride. I know the total mass is that, so I can do 1.056 minus the mass of this over the total mass, and that will give me the percentage by mass of magnesium chloride. And I should get 35.4%. And that is the end for this paper, section A.